So today we are going to discuss a very fundamental and very groundbreaking research paper in the field of quantum key distribution. So what is quantum key distribution? We know that quantum key distribution is a method to securely distribute the encryption keys between two parties through the use of quantum states. So the title of the paper is Quantum Key Distribution Using Gaussian Modulated Coherent States, and it is a paper that published in 2003 in the Nature. And uh, it is written by the main author of this paper is the Frédéric Grosshans and their collaborators, and these people have done very great job in the field of quantum information. So historically, people have introduced the quantum key distribution protocols using the photons like BP84, B92, or E91. That is the entanglement-based protocol. But it has the protocol based on these photon detection is has many limitations as the limitations are technological and as we do not have that much sophisticated operators for the measurement and detection of photons, and that's why we have very low key rates using these kind of protocols. So these people introduced entirely new protocol based on coherent states. The coherent states, we know that in quantum optics are the states of the light that have precise phase, but the fluctuations of the photon numbers uh, is very great. So we can make use of these coherent states, and these are readily available in the form of the laser pulses in laboratory, and the detection scheme is quite suitable and quite simple. So these people introduces the quantum key distribution protocol using these coherent states. So Gaussian modulated is the coherent state, that is, they modulated the phase and amplitude that are the two conjugate variables of these states, uh, and they modulated it through Gaussian random numbers. So using these Gaussian modulated coherent state, they distribute the key between two parties, namely Alice and Bob. So moving on to the abstract, they first talk about the alternative of the photon counting as the quantum continuous variables of light, and said that it is more advantageous over the single photon counting uh, as we have higher key rates uh, with these uh, uh, with these coherent states. And they used only mainly two components in order to complete the whole process. And the first one is the Gaussian modulated coherent state, and the detection system is the homodynamic detection. So they make use of the reverse reconciliation scheme, that is classical post-processing technique they in which the uh, measures the data, and Alice has to estimate what Bob has measured. So this technique has uh, much more efficiency, has much more advantage over the direct reconciliation technique, as in this technique, in the reconciliation technique, that is often called DR, in which uh, Bob has to estimate what Alice has sent. So authors are saying that the RR technique, that is the reverse reconciliation technique, is much more advantageous over the DR because it is much more simple uh, estimate the Gaussian modulation of the Alice on the coherent state rather than to control the entire error detection error introduced by the Bob's apparatus. So this gives this gives some advantage of the reverse reconciliation over the direct reconciliation scheme. So next, they talk about the uh, key findings of their experimental work. That is, they uh, managed to distribute the 1.7 megabits per second key for a free loss line and 75 kilobits per second for a line with losses of some some intensity drawback, that is the 3.1 decibel. So this is the abstract, and moving on to the introduction of the paper, they talked about the use of the electromagnetic field amplitudes, that is the phase, and the conjugate variable, that is the amplitude of the light pulses, in order for the uh, use of the key distribution instead of using the photon counting schemes. So they also talk about that we do not have to use any squeezed or entangled light in order to distribute the key between two parties, as their security uh, analysis is equivalent to the coherent states. So coherent states are much more readily available and much more easy to generate. So we usually use the coherent state instead of the squeezed or entangled light in our protocol. So both have same security analysis. So we usually prefer to use the coherent states. So they talk about the security of the protocol of the Gaussian modulated coherent state protocol under the individual attack, as it is protected by the no cloning theorem of the continuous variable. So we have to use the non-orthogonal state in order to have a security bound on our protocol. So non-orthogonal states are used because in order to get some information, Eve has to measure the incoming state. But when she measures the incoming state, it disturbs the state of the quantum state, and this introduces some errors and noises, and it could be detected by these kind of errors and noises. And Eve and Alice and Bob can use some error correcting techniques and some privacy amplification to eliminate these errors and eliminate the information that is stolen by Eve. And this gives us the advantage to use the non-orthogonal states over the orthogonal states. So moving on to the cryptographic security, that is we have discussed, and it has strong relationship with entanglement. And then they talk about again the use of coherent state QKD protocol and how Alice and Bob are making use of it. So they have used in their experimental setup the reverse reconciliation protocol, as they talked about its advantage over the direct reconciliation scheme, and they said that their practical limitations is only technical. So as we move on to the recent years, we will have uh, much more sophisticated apparatus, and we could overcome these practical or technical limitations on our apparatus. So next, they talk about the whole protocol and the steps that one has to follow in order to complete the whole process. So the first step is on the Alice side. That is, Alice has to generate two random numbers that she denote that he they have denoted with the XA and PA, and they are taken from the some Gaussian distribution with a mean zero and some variance that they have called VA, and not where and not is some short noise, that is the intrinsic noise uh, in the quantum regime. And then the Alice encodes these random numbers into the phase and amplitudes, that is the conjugate continuous variables of the light, and send these light pulses to Bob. So Bob, on the other hand, measured these quadratures. Uh, Bob can measure either X or P of the light pulse, and then after completing the whole process of transmission and measurement, they communicate with through the public authenticated channel and remove the errors, and the resulting correlated Gaussian variables are key elements, and these key elements are further refined in order to then make use in the encryption schemes. So classical data processing starts with the comparison of sample key elements in order to estimate the error rate and the transmission efficiency of the quantum channel. So the observed correlation, that is the common data of the Alice and Bob, is called mutual information and is denoted by IAB or IBA, respectively, for the direct reconciliation and reverse reconciliation scheme. And they can also estimate the Eve's information on the Bob or the Alice data, and it is all denoted by IAE and IBE subscript. So the common secret key that they can use for the encryption purposes is the subtraction of their mutual information from the Eve stolen information, and it is given as the secret key rate uh, in simple or technical terms, and it has units of bits per key element. So classical communication uh, is takes place on the authenticated public channel, and it could be our internet or email or any other medium that we use usually. But quantum transmission of the quantum states usually take place in other medium, like it could be vacuum, air, or fiber optics. So classical communication uh, takes place through the public channel, and it has two steps. That is the reconciliation step, in which we as the Alice and Bob estimate the errors and the transmission of their quantum channel, and after that they use privacy amplification in order to eliminate the Eve's stolen information and in order to maximize the entropy of the secret key, as it should be completely random, and Eve should not have any part of the secret key. So it is usually done by sliced reconciliation algorithm that in which of the details we will not go in this video. So so then they talk about the reconciliation protocols and direct reconciliation and their advantages, and they talk about in this line that this turns out to be particularly well suited to QCV QKD because it is more difficult for Eve to control the errors at Bob's side than to read Alice's modulations. They are talking about the advantage of the reverse use of the reverse reconciliation in the QKD protocol. Then they talked about the privacy amplification, as uh, it is used to filter out the whole information of the Eve that she has stolen in the whole process. And yeah, in order to do security analysis, we have to estimate the Eve's information that she has stolen in during the whole process of transmission of the quantum states. So uh, in order to get the information about the secret key that Alice is sending to Bob, uh, Eve has to intercept the incoming in quantum states, and uh, she done she did she does it with the help of entangling cloner. So entangling cloner is a very nice technique, and it is done by the beam splitter. And in order to implement this attack, Eve has to place a beam splitter in the quantum channel, and she inject another beam into the beam splitter, and the input beam and the beam incoming from the Alice gives us two outputs from the beam splitter, and the author have mentioned that the input field quadratures are denoted by x in and p in, and the output field quadratures are described by xp bp and xep. So one output is allowed to transmit to the Bob, and the other output is of the beam splitter is taken by Eve for her estimate on the secret key. So uh, Eve's whole aim is to minimize the deviation between her data and the Bob's data in case of reverse reconciliation. So these the division is shown by the conditional variances, and these has to be estimated uh, from the perspective of the Eve. So author have shown mathematical in methods that these variations on conditional variances on the Bob's data by Bob's data by Alice and Eve follows a uncertainty relation, and this says this uncertainty relation that Alice and Eve cannot jointly know more about Bob's conjugate quadrature than is allowed by the uncertainty principle. So if but so if Alice has much more correlated data and much lesser deviation in the data between uh, in the data between in her data and the data of the Bob, then there is much more deviation between the Bob's data and the Eve's data. So this is the one-to-one correspondence between these two values. And in order to estimate the Eve's information, Alice has to estimate her information on the Bob's data. So the quantum channel is described by the linear relations, that is relating the Bob's quadratures with the input field quadratures, and the overall noise, that is the channel noise, is denoted by chi x and chi p for the respective quadratures. So so in this line that is highlighted by blue, the author are arguing that the values of the quadratures that they have that the Eve and Bob has measured only depends upon the density matrix Tn, and does not depend how uh, the quadratures values are distributed uh, between two parties. So either it could be a Gaussian mixture of coherent states or any two entangled beams. Uh, it doesn't matter because after all we are only dealing with measured values. So in theoretical analysis, we usually use the entanglement-based protocol in order to do security analysis and for its simplicity. So, so the conditional variance of the Bob and of the Bob on the Bob data by Alice is given by this in equation 2. So in the case of the coherent states that Alice has sent, and these inequalities changes into this given by this. So we can use the uncertainty principle in order to estimate the Eve's quadrature, Eve condition variance of the Eve's quadrature on the Bob's quadrature by use of these values in equation 2 and 3. So Eve's quadratures are given in equation 3, and these are calculated by using the Alice variances in equation 2. So in order to estimate the secret key rate, we have to make use of the Shannon's theory of Gaussian for Gaussian additive noise channels. So first we have to calculate the mutual information between Alice and Bob, and this is given by variances of the Bob and over variances of the Bob condition on Alice, and uh, we can calculate it easily as we have calculated all these quantities before. And Eve's total information is given by this, and it depends upon the Bob's quadrature variance and the variance of the Bob's quadrature condition on Eve. So we know that Bob's quadrature variances are given as this, and their conditional variances on condition on Eve's information are given as this, and we can calculate the overall secret key rate that is given in equation 5. So in order for the security to be guaranteed, it must be positive. And this gives us some kind of implications and some kind of conditions on some parameters. So we have two types of noise, that is the vacuum noise, as it depends upon the line losses, and excess noise that is other than the vacuum noise. So in order to be protocol to be remain secure, the excess noise, that is some noise from some untrusted sources, should be very less and should not be too large. But authors are arguing that for the direct reconciliation protocol, the channel noise should be very less, but uh, excess noise could be large, and we will have uh, much simpler and much secure protocol than in this case. So direct reconciliation technique is usually used in the channels where we have much high transmission, but there is much more excess noise in the quantum channel. So then they talked about the experimental implementation, and they used 120 nanosecond coherent state pulses, and uh, the wavelength is in visible range, that is the 780 nanometers, and they have sent 60,000 pulses for this whole process and to do security analysis, and they have used to make use of some kind of parameters related to the efficiency of homodyne detection, and it is electronic noise and some intrinsic noise of the homodyne detector. So this is the whole process, and they have given in this paragraphs some parameters that they have used. So that is the optimized parameters for the optimized security level, and they have argued in the at the end that in photon counting QKD, the key weight is limited by the single photon detectors, in which the avalanche process are difficult to control reliably at very high counting rates. In contrast, homodyne detection may run at frequencies up to 10 of megahertz. So they are describing the the advantage of the whole process over the photon counting pro based protocol, and uh, they have said that we can make use of these high key rates and by using the more Gaussian modulated coherent states, and this can be implemented based on our present day technology. So uh, that's why we have so many advantages of the Gaussian modulated coherent state based protocol over the photon counting based protocols. So they have shown uh, us in our some figures that okay, this is experimental setup and some relationship between the quadratures of values of Alice and Bob. That is the direct relationship between them. And in this figure 3, they are showing that the noise decreases as the transmission of channel increases, and that's it. So in the method, they are just doing some theoretical analysis about Heisenberg relationship between between the conditional quadratures values, and they talked about some experimental setup, and then they talked about some secret key distillation techniques. So the basic idea of the whole paper is that we can make use of the coherent state, that is the laser pulses, and we could make use of the continuous variables of light in order to distribute the key, and it is much simpler and much more efficient than the photon-based protocol. So that's it for today. Kindly, if you like the video, please thumbs up and share the channel and also subscribe it.